can go till the end of the hour here. So the next
Okay.
50, the next 59 are all yours. Hello, everyone. Welcome to today's webinar. Happy Tuesday. Good morning, good evening, good afternoon, wherever you are in the world. Thank you so much for joining us today. We are just 1 minute past the hour here, so we're going to go ahead and get started. I'll expect to see a few more people trickle in. I know our system is having a little bit of an issue right now getting some reminders with people's join links out. So if you're here, I'm glad you made it. If you're watching on the replay, I'm so sorry about the issue, and I'm working to get as many people in as possible. My name is Heather Grant. I am one of the community admins here at the Maintenance Community by Upkeep. Thank you once again for being here. If you are not already a member of the maintenance community on Slack, we would love to have you join us. I will add the link on how to sign up in the chat in just a moment. Today I have with me Jonathan David joining for a presentation on the fundamentals of a failure-free operation. I am looking forward to learning a lot. The recording from our session today will be available in the maintenance community Slack group tomorrow, along with a copy of the slides that you see here today. Jonathan himself is actually also available to answer questions live in the Slack group, so please feel free to share the recording of this webinar or the invitation to Slack with friends or colleagues or anyone you know who would benefit from hearing some of Jonathan's expertise. Final piece of housekeeping before we get started, you'll notice that your cameras and microphones are not turned on today. So what you want to do if you want to ask any questions of Jonathan or answer any that he may ask of you is please use that chat feature on the right-hand side of your screen. I believe somebody is saying hello in there already. Yes, hello, hello. Feel free to say hi, introduce yourself, and let us know where you're joining from. Chat your questions as they come up throughout the presentation. We'll do our best to answer as many as we can at the end of our time today. But anything we don't get to, we'll answer offline in the community as well. That is it from me. Thank you again, Jonathan, for being here, everyone else for joining as well. And Jonathan, I'll turn it over to you to get us started.
Okay, fantastic, fantastic. Heather, thank you for having me. And again, like I said before, thanks to everyone at Upkeep for putting this together. I really appreciate the opportunity to come on the platform today and share a little bit of some of the things that fascinate me as I go along in my career. Okay, my name is Jonathan David. I've spent the last 15 years in the maintenance industry, maintenance, reliability. I started out in renewable energy. Okay, I did a couple of years there, I think about 4 years thereabout, and then I switched into the oil and gas industry. I also had an opportunity to do a little bit of work in manufacturing very, very early on in my career. I am during one of my internships, and I think having spent a little bit of time in these three industries have given me several perspectives as to how our job as professionals work. I think I've been able to see the upsides and the downsides. I've worked in areas where we're totally reactive in our work, and I've also worked in areas where we're top notch, we're proactive. We have lots and lots of process to make sure that reliability is guaranteed in our operations. In all my time, I don't think I've seen a perfect organization that has it all together. But I think I've been able to see organizations making progress, and I see organizations putting together processes that makes for continuous improvement. And for me, what I think when it comes to maintenance and reliability is it's a continuous journey of improving day in, day out. They say the day we stop learning is the day we die. So basically, if we're going to operate at the level where we are reliable, where our assets give the value it's meant to give, then what it means is we have to continue learning. So I'll congratulate you for being part of this event today. It means you value your learning. It means you want to improve. It means you take this journey of improvement and reliability is very, very seriously. And that's why you're joining us today. So welcome again to this session. By no means I'm no island of knowledge. Neither am I a well of wisdom, of all the wisdom that exists in the world. Just like yourself, I'm a professional. Just like yourself, I learn. And that's why I'm here today, to share some of the things that fascinates me with you. So earlier, I think late in 2020, I think I stumbled upon the concept of what we call failure-free operations. But before I stumbled upon the concept of failure-free operations, I think I came across that while I was doing probably a little bit of research work. Before then, I had been fascinated about the concept of failure, and I'll tell you, I'm usually fascinated about the alternate things, right? So, for example, while a lot of people study reliability, I study the opposite. I study failure. While people study leadership, I study the opposite. I study what people don't look at. I study followership. Because what I discovered is the key to getting what we desire is looking at the alternates. It's looking at those areas we think are not very, very important. So a lot of the time we spend a lot of time studying about reliability, looking at how we can become reliable, how our plants can become reliable, how we can get the best value from our operations. But I think that value comes from looking at the alternates. The alternate in this case is failure is what we are trying to prevent, right? So I believe that if we have a deeper understanding of failure, of how components fail, of how equipment fail, that's going to help us a lot in making sure that we become reliable. If we eliminate failures, naturally reliability is the end result of eliminating failures. So you're going to see me take a different standpoint instead of breaking down what reliability should be and how we can achieve failure-free operations. You're going to see me talking about failures instead. And I understand that if we get, the more we know about failure, the better we get at being reliable. Okay, so let's start with failures. So why failure? Some of you, if you were attending any of my webinars before, you might have heard me talk about failure. So the question is, why failures? The reason is, bottom line, failure is the central thing in our operations, whether you work in manufacturing, you work in utilities, you work in oil and gas, you work in renewable energy, you work in the service industry, you're providing a service, your software, yeah, you have maybe you sell some softwares for us, maybe a CMMS software or something for us in our operations to help us do a better job. Failure is a common thread that runs from the C-suite in our organizations down to the shop floor, to the lowest persons. Failure is what troubles our bosses, the MDs, the CEOs. If we're having failure, failure is a nightmare of managers, right? Failure is how our success is measured, by the way, right? How well we do is basically a consequence of how much failure we've been able to avoid or how much failure we've been able to take away out of our system. So at the end of the day, when you are congratulated to say, when you get that congratulation or that handshake or that plaque that says, congratulations to the maintenance and reliability team of company XYZ, what they're actually saying is, okay, congratulations, you've been able to kick failure out the door, right? So, and failure also determines our profit levels in our organization or the lack of it, right? The more failure we have, the more money we lose, the less profit we make, right? Failure, we cannot wish failure away, right? Failure, we cannot wish it away. Failure is some of the reasons why we even have a job, by the way, to keep the plant running, okay? And yes, there's that saying that if you leave an equipment to save itself in its natural state, degradation will happen. If you leave a house unattended to for years, naturally, degradation will begin to take place. So failure is basically a fundamental part of our life, and it's a fundamental part of our being, of our existence. Even as humans, right? When we live, as we grow older, what happens? At some point, failure begins to happen in our system, right? As we grow older, naturally, you get to some point, they say, oh, your digestive system is not what it used to be, your strength is not what it used to be, so maybe you got to slow down, you need to change your lifestyle, you need to do this, you need to do that. What we're trying to do is basically saying, hey, we're getting older, and failure is going to creep in at some point, and what do we do to be able to live the long life we ought to live? It's not different for our assets, right? We're looking at failure and we're saying, oh, we don't want to fail so that we can make more profit so that our goal of setting up this organization will be achieved, right? Every asset we possess in our organization has has just one goal, and that goal is value. That value addition for most organizations comes in the form of profits. Every organization exists to make profit. So like it or not, yes, we know we have a few other kind of organization, but for most of the kind of organization we work in, right, naturally what the board members are looking for at the end of the day is not just that maybe we work safely. It's not just that, okay, we save the planet. Ultimately, in addition to all those other beautiful things, we need to basically have return on investments for the people that have put their money together to say, okay, we want this organization to run. Okay, so every asset has that purpose to add value, to bring value, and to create value. And every single strategy we take, whether it's at the boardroom, whether it's on the shop floor, whether it's in our workshops, whether it's sending people for training, whether it's buying a software, whether it's employing a consultant, every single thing we do is geared toward making sure that that value is achieved. But on the downside, failure is one thing that can threaten that value that we're seeking to share, that value we're seeking to bring. Failure can threaten that, and that's why we see failure as the enemy, right? But someone would ask me, so what is failure? One thing I've been able to think about in my career and in doing some form of research is to be able to look at definitions, and definitions have a big impact on how we react, right? So there are certain words you are going to use, and those words are going to trigger certain reactions, right? So if you define failure the right way, you will be able to see how you define it will determine the action you would take toward preventing failure. If in your organization you decide to probably go on with the typical saying that, oh, every equipment will fail whether you do something about it or not, what that means is you've trivialized failure, and there's a very high chance that you're going to tolerate failure in your plant or in any equipment that you're meant to manage. So equipment failure for us, defining equipment failure is critical to whatever strategy you put in dealing with failure. Okay, so for me, the way I define failure is this, right? Equipment failure, it basically means an equipment not being able to perform its intended purpose, its intended task, right? That equipment might have stopped working completely. That equipment might still be functional, right? It might still be doing some bit of work, and it might simply mean that equipment is not meeting its target expectation. So I'll give you an example. In some scenarios, right, you're going to find out that until an equipment breaks down, it is not referred to as failure, right? Until an equipment breaks down, maybe it's taken out of service, it goes out of service and results in some major loss, it's not regarded as breakdown. People tend to see breakdown as failure, but they don't tend to see other faults that come up in an equipment as a failure. So I'll give you an example. For me, these 4 branches you see on your screen represent what failure is for me, right? The equipment does not work at all. For me, it's failed. When equipment does not meet quality specification, it's failed. And you can do your research about this. These are basically some of the key things you can use to define failure. If it doesn't meet safety specification, it's failed. If it doesn't meet your throughput, so an equipment is performing at 75% of its capacity, it's meant to do 100%, and that is what is required of it, but it's unable to do it probably because some component is bad, something is worn out. It's failed. It's still giving out product, but that doesn't mean it's meeting the expectation. So when you define reliability, there's a limit to it. When I mean there's a limit, there are terms and conditions under which you define reliability. You have to specify, okay, the conditions, right, under which reliability is defined. So reliability, when you define reliability, you're going to say an equipment performing its intended function under specified condition, right, and over a given period of time. So if you define failure also, you have to define it with terms and conditions. And in my opinion, and for my research, this 4-pronged approach gives you the typical terms and conditions under which you can define failure. And I'll tell you why I define failure in this way, right? That's because as much as we talk about equipment failure, as much as we talk about equipment failure, most equipment, right, don't just fail, right? Equipments are made up of components. So naturally what happens is the component parts of that equipment fail. So failure should actually be treated at component level, not necessarily at equipment or at system level. So yes, we're going to talk about system failure, but system failure starts at component level, right? So when I define failure, as much as I'm talking about an equipment, there might be some components of that equipment that has failed, but that does not necessarily take it out of service, but impedes it from performing its function 100% the way it was designed to do, provided all the stated conditions for which that equipment is meant to perform that function is at play, right? So the question is, what happens when failure happens? When failure happens, collateral damage is what happens. Collateral damage is basically, so you could see some of the pictures on your screen. I'll give you an example. If you have a bearing, right, that is bad, what happens is the bearing is bad. There's a chance that if you allow it to get to the point of breakdown or total functional failure, where the function can no longer be performed at all, what happens is you might not end up changing just the bearing. Okay, a shaft might be damaged, a gear might be damaged, and equipment might be put entirely out of service simply because there was a bearing failure. It started as a component level failure, but because it's not been picked up, it's not been detected, it's escalated to a complete failure of the equipment and results in collateral damage. The question is, can you afford this? Now, this is one slide I like, right? Our goal is to eliminate failures. Our goal primarily is to eliminate failures. That's what we want to do. And the only way we can eliminate failure or reduce failure is by understanding how equipment fails. I'll give you an example. I like real life example. I don't have to always give technical examples. So, for example, it's been a tough 13, 15, 18 months because of the coronavirus pandemic, and it's been a tough one for all of us, right? But despite the fact that it's been a tough one for us, the key to finding the vaccine that is going around the world now starts from studying the virus itself, right? So to find the cure, you study the virus. It's the same thing with our equipment, right? To find the cure for failures, the primary thing we have to do is to understand how this equipment fails, is to understand how these components fail, and then from understanding it, we can learn and develop ways to predict, prevent, or eliminate the failures. It's exactly the same thing. We get all kinds of vaccines in our bodies over our life, right? There's the vaccine for polio, there's vaccines for yellow fever, all kinds of vaccines exist. What do the vaccines do? Because we've been able to study how these diseases are born, we've been able to study the pathogens, we've been able to study the means of transmission. What we've simply done is we've been able to design vaccines that help us, that even if you come in contact, you don't get infected. It's the same thing for our equipment. Whether you're talking about a pump, you're talking about a turbine, you're talking about a motor, whatever you're talking about, it's the same principle. Understanding how failure happens will give you a huge leverage in knowing how to manage failures and in knowing how to eliminate failures. But here's a twist. For most of us and for most of our careers, we've seen failure as the enemy. And from the discussions I've been having here right now, there's a chance you see failure as the enemy. But let me tell you something. Failure is actually not the enemy. Our real enemy is the consequences of failure. So if I back up to the previous slide, if the bearing will overheat, and if that, no matter how that bearing overheats, it's not going to result in any form of damage to the equipment. It's not going to result in any loss of production. There will be zero impact if the bearing damages, if the bearing goes bad. Then we don't have to bother about it. That's why parts. That's why a valid strategy actually dealing with some form of failure. There are some equipment that we say they are maintenance free. What that means is some equipment will say the strategy we utilize for them is run to failure. What that means is we've looked at this equipment and we say if it goes bad, there's no safety, there's no consequence safety wise. If it goes bad, we don't lose any bit of money. If it goes bad, there's no reputational damage. If it goes bad, there's no asset damage. So if there is no consequence, failure becomes tolerable. So note, the enemy is not failure. The enemy is the consequences that come because of failure. And most times, these consequences are not consequences we can live with, right? Some consequences are so devastating that for generations, right? For generations, people are left scared, right? That for generations, communities will find it difficult to even recover from those consequences. So, for example, if you have any experience in oil and gas, like I do, you would know that it's a volatile environment. You work in a gas plant, you work in an oil plant, you know it's a volatile environment, and that is not one area you want something to go wrong and the plant blows up in your face. Or if you work in a nuclear plant, that's not a place where you want to work and something blows up in your face, right? So our enemy is really the consequences of failure. So let's talk about failure-free operations, right? So failure-free operations is not it's nothing new, right? Research started about on the concept of failure-free operations in the 90s, and it's been primarily tailored around the aircraft industry. And I think most of the areas where this research has taken place, it has been always been primarily around aircrafts and also primarily around military hardware, but mostly military aircraft. But where I'm going to is not it's that these principles can be applied to most of the operations we have, because whether in an aircraft or in a refinery, a pump is a pump, a motor is a motor. They might not be performing the same function. A turbine is a turbine. They might not be performing the same function, but the principles are basically the same. So these principles are applicable. So you might want to ask me, so what is failure-free operations, right? It's failure-free operations is practical. It's just the way it is. It's basically literal, the way you see it, right? Failure-free operations. Operations without failure. But something to note, failure-free operations is not indefinite. Just like I talked about the definition of reliability, right? Failure-free operations has its own terms and conditions, right? So if we're looking at failure-free operations, it means there's a time limit for it, right? So failure-free operation must have a period to it. So when you see the definition, you are definitely going to see it as FFOP, failure-free operation period, and you're going to see another one, MFOP, maintenance-free operation period, right? And what it simply is basically a period of time during which no failures resulting in a loss of system functionality occur. Note, there's a caveat to it, right? No failures resulting in a loss of system functionality occur. Okay, so now what this means, I'll explain in the next slide, right? And then obviously closely married to failure-free operations is maintenance-free operation periods. And basically these are measures of reliability and can be used to replace a typical mean time between failure. I'm going to break this down shortly. Okay, so now, why is maintenance-free operations tied to failure-free operations? Naturally, we know that maintenance is the means with which we restore functionality to an equipment. It could be scheduled maintenance, it could be unscheduled maintenance, it could be condition-based maintenance, but anything you do about maintenance is basically a task for restoration. So here's what we're trying to achieve with failure-free operations. We want a period that we can predict that an equipment will run, will work, will perform its function, will perform its mission, and nothing, right? Nothing would happen that would impede its mission during that period. And that failure-free operation would naturally transform to a maintenance-free operating period. So when there's no failure, right, maintenance would not be required for that equipment, but we have a specific period for that. So what does this mean? It means it doesn't necessarily mean a fault might not happen in that system. But what we're saying is, if any fault should occur during that period, it should be absorbed by the system without losing function. The fault must not lead to a system failure or a mission failure. Even if the fault is developed at first use, so let's say we'll specify, we've looked at it, we've designed this equipment, and we'll specify our maintenance-free operating period or failure-free operating period as, let's say, 6 months, 6 calendar months, right? Even if a fault develops in, let's say, a 6-month period started from January to June, even if the fault developed starts in January 1st, right? The system must be able to continue operations till June when we are ready to take it out of service for maintenance, right? Any envisaged maintenance would be handled during scheduled maintenance or inspections. This looks, to some people, this might look funny, it might look like, is this possible? But I can tell you that this is possible. I'm not teaching you something new. This is not a new concept that has just been born. It's something that has been around for a while, right? So how does this play with mean time between failure? Because I'm sure you have seen the reference. So for mean time between failure, most of the time, we look at an equipment, right? And based on the design, what we're trying to do is extend the time as much as possible such that the time in between failures is as large as possible, right? And then the recovery period is very short. However, it's difficult for you to predict mean time between failure for some equipment, right? But when you design an equipment with failure-free operations in mind, you can be able to predict. You know, for example, going back to our 6 calendar months, you know that for 6 calendar months, right, this equipment can run without any interruptions. But for our mean time between failure, most of the time, we react to the information, right? We'll take the information. I used to do this before now. We take the information and we look at it and we'll say, okay, we're calculating the mean time between failure for this equipment. Oh, it's too short. What can we do to improve? Mean time between failure is great, but in a way, we react with the information, except in cases where you have manufacturers that have this as part of their design. And even if an equipment is designed with certain mean time between failure, in my experience, and I think it might be the same in yours, you cannot count on that mean time between failure when it comes to your operations. Okay? Now, if we have our failure-free operation, definitely there has to be a time to maintain that equipment. And the maintenance time, that scheduled maintenance period for that equipment, we'll take it out of service to restore it, is what we refer to as our maintenance recovery period. Now, our maintenance recovery period is now directly dependent on the length of time we have that equipment in our failure-free operating period. Now, what does that mean? It means if I have an equipment that, let's say it was specified, can go 24 calendar months, for example, without maintenance, it means that by the time I take that equipment out of service after 24 months, if it lives up to that after 24 months, right, it means by the time I take it out of service after 24 months, the amount of maintenance I'm going to do is most likely going to be extensive. than for an alternate equipment that says the main time the failure free operating period is let's say the failure free operating period is a month. It means the chances that the maintenance I'm going to do during my maintenance recovery period at the end of the calendar month is going to be lesser than what I'll do for an equipment that has a longer period of maintenance free operations, right? So, and during our maintenance recovery period, there are going to be different strategies we are going to be applied for different components based on failure patterns. So by the time we are maintaining, we're going to have different maintenance tasks that will be carried out, that will be component focused and system focused. And while we're carrying out that maintenance also, it's also a period of learning as well. So we're looking at that equipment and we're saying, okay, as I'm carrying out maintenance to restore, I'm looking at the components, I'm saying, how has it failed? Right? Did it fail? Did it not fail? Okay, this has been a 24-month period. What's the level of degradation? What am I doing with all that information? That information I'm going to feed back into the system to be able to improve our system. What that would do is I might look at it and say, okay, this component deteriorated quite fast. This one was quite slower in how it deteriorated. So that means this one will last longer, and then maybe we can feed that back in to our partners and get some improvement. Now, where does this apply? So primarily, this is going to apply a lot when it comes to design stages, when it comes to product design. It's going to apply. But when we look at every asset, we have to look at the entire lifespan of the asset, right? So for beginning stages of project, we're going to look, this is part of what, let's say you're a feed engineer, this is one thing you want to look at. If you're a project engineer, this is one thing you want to look at. It doesn't mean you intend designing the component yourself, but backed with this kind of information, you're going to make better decision in your equipment selection, right? You want to look at equipment that are built much more robust, that can go longer without failure, right? And you want to look at the trade-offs. So you're not going to go into the market for equipment selection based on pricing. What we are looking at in this case is you are going to go into the market for equipment selection, and what you'll be looking at is lifetime costs, right? Life cycle cost. That's what you'll be looking at. When you're looking at it as life cycle cost, your cost of acquisition might jump because maybe you are getting something much more better, but you are going to find out that your cost of operations will drop drastically to balance it out. And that way you're going to have less troubles when it's time to run, when it's time to operate. Okay. Now, when it comes to the building and commissioning stage, you're going to also see that when you are building, when you are installing, when you're inspecting, when you're commissioning, you're going to look at this same equipment and see, gather what information you can gather. During operations, we're going to gather that same information. And if we're a learning organization, we're going to feed this back into our system for our next round of acquisition, or our next round of upgrade, or our next round of improvement. So it's basically the cycle continues. Okay? So how can this strategy work? We say it's a bottom-up approach. We need everybody to be on the clock for this one. We have to start by clearly understanding how items fail, how components fail. Okay? And obviously, if you've done anything around RCM, definitely discussions around how a component fails will definitely come. Will you ask yourself that question, how would this item fail? Because what you are doing in that case in RCM, you're trying to put a strategy in place to combat that failure. But now, note, this is not RCM. So we could be looking at how can an item fail in order to improve, in order to make that could help us make a better buying decision to say, okay, if I have an equipment that fails this way, maybe we don't want an equipment that will fail in this format in our operation. Let's say we have an equipment that fails by blowing up, right? And then I'm working in a volatile environment. I'm working in an oil and gas facility. I'm working in a gas plant, for example. I don't want that kind of equipment, because if I have that kind of equipment, any ignition source will be catastrophic, right? So, but let's say I have something like that, and maybe when it fails, it flames up, but I work in a water plant, it might not be so critical for me to look at it in that light. So these are things to look at, right? So what, apart from understanding how an item fail, we also have to understand why the item fails. So you see, we start with how, we go to why, and then we look at the equipment, the item, and we'll say, is there a way to accurately predict when, not the word when, they will fail? So we don't just say how and why. How and why, how is a typical question that will happen as part of your RCM, right? But by the time you dig into why the item failed, and you dig into when, being able to predict when, because you cannot predict when it will fail, you cannot predict your failure-free operating period. Then we have to be able to gather available data on environment. We have to localize it, right? If I have an equipment that is built in the United States, right, I have to be able, if I want to pick that equipment and use it, say, in Dubai, I have to be able to note that the operating conditions in Dubai are absolutely different from the operating conditions in the United States. Ambient temperature is different. It's also different if I take that equipment to Canada, right? It's different if even within the United States, it's different if I take the equipment to, say, somewhere like Alaska, or you bring it to a tropical region like Nigeria, where I'm based from. So you have to also have localized data, okay? Then we have to be able to look at that component and say, what are the early stage failure? What are the indicative characteristics of early stage failure? And also determine and understand the causes of unreliability or failure. And then we'll see how can we eliminate or how can we control them. Okay. What are the pillars? What are the pillars or systems that can help us really achieve this? Condition monitoring is a big deal when it comes to talking about maintenance-free operating period. Redundancies are a big deal when it comes to talking about this. Reconfiguration, right? It's a big deal when it comes to talking about failure-free operating period. Advanced diagnostics, prognostics. I won't have time to break all of this down, but definitely, if you want more information on this, you can just hit me up afterwards. I'm going to provide you details and provide you some reading materials that can help you break down all these other pillars that I've just mentioned there. I won't be able to break all of them down here, but these are some of the pillars that can help you. I know most of us will be familiar with condition monitoring. Most of us will be familiar with redundancies. One of the ones I love is reconfiguration, right? Having an equipment, okay, maybe there's a fault, but you are able to recover without going offline, right? It could be a form of redundancy. It could be a form of software redundancy. It could be using voting codes as well, right? You have a system, you have a computerized system, you have a software system that says, okay, if such and such is the condition, take this action. So you have a voting system that automatically probably overrides the fault area, and then system function continues without going offline. Okay, so these are some of the pillars, and I tell you, just reach out to me. I'm going to share some literature with you, and then there's so much that we can learn from this and begin to see what areas we can apply. Okay, I'm running out of time, so I'm going to just I'm almost done, by the way. Okay, so what are the impacts? How does this benefit us, right? What this does is, if you are up, let's say you are a feed engineer, or you work in a plant that you manufacture equipment, it's going to help you focus on reliability during your designs. So you want to be able to make components or buy components that are more resistant to failure, that are more resistant to defect, that are more resistant to degradation, right? It requires a lot of integration between suppliers and customers, right? Because customers would need to be able to provide a lot of operational information to help suppliers make the right choice of equipment, right? Failures will be significantly reduced naturally. So if you're able to predict your failure-free operating period, I'm sure you want a longer failure-free operating period. And naturally, what will happen is cases of random failures will reduce. Okay, cases of random failures or constant failures would reduce in your operations. Okay, you can debunk that because you know you can trust this equipment. Uh, there's going to be a lot of increase in your operational effectiveness. Your operators can work and produce at maximum capacity. Okay, and then they only have to go offline at scheduled period of times, right? And becomes very easy for your supply chain. I know MRO is a big deal for lots of companies. This I've had my own experiences there, right? When it comes to MRO. So, but supply chains become very easy because we can predict when we would need what, and we can plan, and then we don't need to have emergencies, right? Our cost of repair will drop, and then we can plan based on reliability predictions. A few notes: if you're going to be applying some of these principles I'm sharing, there will be a possible increase in acquisition cost as a result of more rigorous design processes. So, for example, if you're going to buy let's say, for example, I have a centrifugal pump, and let's say I want the centrifugal pump that the rotor is much more resistant to wear and tear. What that means is the designers might have to use a different material to design that rotor, right? Or so some manufacturers or for manufacturers already have this. If you go to them, they are going to tell you, okay, we have this grade, it's more resistant, it's for this application. This grade is it's probably less resistant, it's for such and such an application. Naturally, a more resistant rotor would most likely be more expensive, right? So it's going to be, there might be a little bit there might be a jump in acquisition cost, right? Well, we need to also study the trade-offs between the investment and the operational consequences of poor equipment reliability. So if the failure you're trying to prevent, the consequence of the failure is if that failure is inconsequential, there's no point trying to invest in this area when the failure is inconsequential, right? If the result of that failure has no bearing, it's what we would save if that failure happened is basically it's not worth investing that money. Then there's no need to do that. So you want to apply this. Yes, RCM comes in. Yes, criticality ranking. You have to basically rank your equipment and then know where am I going to. What's my most critical equipment that has the most consequence if they fail. And so if I do this, I think I'm going to. There has to be a return on investment for it, right? So it has to be a logical integrated approach to reliability. It's targeted. And the target of this is to achieve high accuracy system reliability predictions, and also help increase our operational availability and also reduce life cycle costs. I said that earlier. It focuses on causes of failures and their elimination rather than measuring and responding to their effects. So sometimes we study our data and then we respond in typical operations. But in this case, you are going to proactively focus on the causes of failure and then take action. It also provides us greater insight into product design. So you know that if as a team we want to apply some of these principles, what it means we have to study the design of some of the equipment that we want to use in our operations, and better understanding of our design will help us better operate them. And also it helps us better and realistic spares prediction. So we have a fixed period of maintenance. We've been able to achieve failure-free operations for certain equipment, so we know what we need at what time, and then we know what spares we'll need. We're not going to have a warehouse full of spares that we don't make use of that will later sell off. So the question I'm going to ask right now as I close this is, does an understanding of failure help me do a better job? Do you think an understanding of failure will help you do a better job? Thank you. I'll welcome any questions now. I know I'm far gone in my time, but I'll welcome any questions you might have right now.
Awesome. Well, thank you, Jonathan. That was a wonderful presentation. I really enjoyed it. We do have some time left in the rest of our hour here together. So if there are any questions, please feel free to send them through in the chat. I know we got a couple of questions here from Henry. Henry asked, MTBF is a lagging indicator which is deduced from equipment behavior over a period of time. In
Mhm.
comparison to F-FOP, how do you determine the length of time?
Okay, so when we look at the length of time when it comes to failure-free operations, that's why I said if I go back to my slide, I'm not necessarily going to display that now. If I go back to my slide, what we have to do in this case is we're looking at the equipment, right? And we're looking at this equipment at component level, and we study the equipment and we're asking ourselves, how does this equipment fail? Right? We know how it fails, we know why it fails, and that way you now have a component that is designed specifically to resist degradation, to be resistant to defects as well. So naturally, if we go do some reliability analysis, testing is how you determine the length of time for which a component can last. And naturally, if you're going to look at this, then remember I said it has to be an integrated approach with manufacturers. So with manufacturers, with the testing done, they are able to note how long each component can take for it to fail. So at the end of the day, when you look at the length of time an equipment can survive in failure-free operations mode, it's basically a sum of the reliability of the entire components that make up that equipment. So if I have an equipment that has 1,000 components, right, and I've been able to analyze all that components, what it means is I'm able to determine based on that, on the weakest link, the shortest possible time or the longest possible time it can survive without failing. You get me? So that's why I said it's an integrated approach. And that's why a lot of the time, it's going to happen more in design. It's going to happen more when these components are manufactured. So for, let's say you are in the operations, you operate a plant. So naturally, having a discussion with your original equipment manufacturer is a simple way of getting this information, studying their literature, looking at the components. Okay, for example, if you know the components, you know what they are made of, it's going to also give you an indication of how sturdy these equipment are and how long they can last.
Awesome. A similar question just came in from Rupesh asking, is there anything else that distinguishes MFOP from MTBF? Anything
Okay,
else
so here,
to add in there?
so here's what I'll do, right? That distinguishing is a whole lot of literature, right? I already know this was going to happen. Okay, and so it's MFOP. It's not a very popular subject right now. So what I'm going to do, Heather, is for those of you, I know all of you are in the Slack community, right? And I'm going to drop a link there where you'll be able, I'm going to drop a link to a literature where you will be able to read up on the differences between MFOP and MTBF. And then it's going to give you a better understanding of both subjects. Okay. So just expect I'll drop the link later on today, and then you can study it. I have a whole chunk of materials that you can look at and then learn. The purpose of having this conversation is this, right? This might not be operational where you work right now. You might not be familiar with it, but if you understand these principles, there are ways it will help you start understanding the current equipment you work with, your current assets, and how you can improve them. And when you get the opportunity to be part of those, to make a decision on asset upgrade, on asset purchase, you'll be able to do more.
Awesome.
Mm-hmm.
Well, I'll look out for that link too, and I'll be sure to attach it to the webinar so anyone watching the replay of this will be able to go and find it easily as well. Mm-hmm. Bruce says he is leaving to go out the plant. Goodbye, Bruce. Have a good rest of your day. We have one more question here from Henry, and then again, please feel free to send through anything else. Oh, I see one more just came in. But the next question here is, what prediction tools do you use to determine the F-FOP period?
Okay, so when it comes to tools, right, I think it's similar to the first question. It's basically maybe a rephrase of the first question, which I answered. So when it comes to tools, note when you are dealing with maintenance-free operating period, uh, it's not reactive in nature. It's not going to, you're not going to wait. So MTBF, naturally, we go back and we calculate, right? So when you're dealing with failure-free operations, it's something you're going to use, something that's proactive. It's not something you go and determine afterwards. You can determine mean time between failure afterwards. When it comes to failure-free operations, you need to determine ahead of time. So when you are making the decision to say, okay, I need a pump that will be able to go 6 months without any form of maintenance, right? Then when you go to the market to shop for pumps, you go with that information. You send that information to the pump manufacturers and say, I need a pump that can do XYZ period without any form of failure. Now, that would be a layman's terms of telling the manufacturer, I need a pump that can do a failure-free operating period of 6 months, for example. Okay, so it's not reactive in nature. It's not something you determine afterwards. It's something you are proactive about to look out for at the beginning.
Awesome. We got one more question here from Rupesh as well. It says, any hints on how to focus on consequences rather than failures?
Okay, great. So when it comes to consequences, right? It's, let me put it this way. I didn't want to clog up the slide. I had this slide where, I don't know, some of you must have come across it, where we try to break down the consequence of failure. So if you've done anything around reliability center maintenance, naturally, right? Just look for the RCM logic. What the RCM logic helps you to do. So that question is from Ramesh, right? Rupesh. So just look for the RCM logic. If you see the RCM logic table, what it does is it asks a few questions. It says, if if this failure happens, right? If this failure happens, are we going to have maybe a safety insert on our hands, right? If the answer is yes, naturally it's going to tell you carry out condition-based maintenance, do some condition monitoring. And then if the answer is no, it's going to ask you the next question. Are we going to lose production? If the answer is yes, it says do some condition-based maintenance, do have some condition monitoring tools. It asks you the next question: are we going to have some losses in terms of asset damage? Should there be a failure? And then naturally, if your answer is yes, it will still send you to condition-based maintenance, and then also tell you, okay, if there's no condition-based maintenance, do some PMs, right? Maintenance at intervals. And then by the time you ask all these questions, and all the answers are no. So if there's not going to be a consequence in terms of safety, no consequence in terms of no consequence in terms of mission losses, no consequence in terms of asset damage. And so if none of these consequences will apply, naturally you're going to run to the next thing to tell you will be run to failure. So if you want to focus on consequence, it has to be a deliberate action. Deliberate in that if you look at your operations, and let's say you are dealing with a machine, and then you want to look at, okay, failure. Once you look at the failure, your second thought will be go beyond the failure, right? And naturally we do this. So naturally, if you are going to have some form of ranking where you say, look at the criticality of an equipment and say, simply ask, what happens when this equipment fails? What happens in terms of safety? What happens in terms of production? What happens in terms of asset damage? And also you might ask what happens in terms of our reputation, what happens to the environment, right? If when you quantify each of this, go beyond the failure and ask what happens, those are the consequences. And the question is, if you can live with them, then you don't have to bother. But if you know you cannot live with them for any reason, then you have to take the necessary action. So what I'll say to your question is, go beyond the failure, ask yourself the question, what happens afterwards when this thing fails? Don't just focus on how much will it take us to fix it. You have to consider what it will take you to fix, but also ask yourself, what other factors are affected? Those are the consequences. And the larger they are, the more you have to do something to make sure that is eliminated.
It's a great answer. Thank you so much. Really thoughtful answers to some thoughtful questions. I hope those helped answer your questions to those who've asked. I think that'll wrap up our time today. Once again, thank you, Jonathan, for being here. I really enjoyed your presentation. It was awesome having you join us. Thank you again to everyone making time today for this webinar, and I will see you all next time.
Okay, thank you so much, Ada. I appreciate it.
Of course. Thank you.
Okay then, bye-bye.
Bye.